Hello everyone, and welcome. I'm excited to be here today to introduce you to the fascinating world of integral calculus. On this first slide, you see the title, Integral Calculus. There's no subtitle, but what you can expect from this presentation is a quick overview of what integral calculus is all about, why it's important, and how it plays a crucial role in mathematics and real-world applications. We'll walk through the basic concepts, some key techniques, and see how it all fits together. So let's get started and explore the amazing ideas behind integral calculus. Let's take a closer look at some practical examples. For instance, when we want to integrate 4x, we write it in a specific way that makes the process easier. This helps us understand how to handle different types of functions. Moving on, we'll explore the technique of integration by parts, which is a powerful tool when dealing with products of functions. We'll also review the concepts of indefinite and definite integrals, emphasizing the key differences and when to use each. As we progress, we'll see examples that include limits to understand how integrals behave over specific intervals. To help you memorize and apply integration techniques more effectively, we'll go over a table of integration formulas. These are essential shortcuts that save time. And of course, we'll clarify the notation used in integrals, because understanding symbols is crucial for solving problems accurately. Finally, we'll wrap up with the idea of the antiderivative, which is the foundation of integration, and conclude with a thank you for your attention. All these points are interconnected and build towards a solid understanding of integration methods. Let's take a closer look at indefinite and definite integrals. These are fundamental concepts in calculus that help us understand areas, accumulated quantities, and more. When we talk about indefinite integrals, we're essentially finding a family of functions whose derivative gives us the original function. It's like revering differentiation. On the other hand, definite integrals involve specific limits, giving us a numerical value that often represents the area under a curve between 2 points. Recognizing the difference between these two types is key because it influences how we set up and interpret integrals in various problems. Throughout this presentation, we'll see how these concepts are connected and how they form the basis for many applications in science and engineering. Let's focus on a key idea in integration by parts. If we have a portion of the integrand called u, whose derivative is simpler than u itself, then we can assign that to do. The remaining factors, including dx, will form dv. Conversely, if we identify the most complicated part of the original integrand that still fits basic integration rules, we assign that to dv, and the rest becomes u. The main goal here is to strategically choose u and dv so that the integral becomes easier to evaluate. This approach is all about simplifying complex integrals by breaking them into parts that are easier to handle, which ties into the overall theme of mastering integration techniques efficiently. All right, let's walk through this example together. We start with the function v equals e to the power of x, which is written as v equals ex. This is our key function because its derivative, dv, naturally becomes ex dx. So when we differentiate ex, we get the same function back, which makes it a bit special. Next, we see that do equals dx. This tells us that our differential for u is just the differential of x, so do is simply dx. It's a straightforward substitution that simplifies our calculations. Then u equals x, which might seem simple, but it's a crucial step because it helps us set up the substitution. By defining u as x, we can rewrite integrals more easily. And finally, the number 8. Which is just an example to tie everything together. The key idea here is understanding how these differentials and substitutions work harmoniously in integration by substitution. When you see ex and dx together, recognizing that dv equals ex dx helps us see how the integral simplifies nicely. This example illustrates the importance of choosing the right parts to substitute, making complex integrals more manageable. All right, let's look at these derivatives and functions to see how they connect. First, we have v equals sine of x. That's a common basic derivative we use when working with trigonometric functions. Next, v equals negative cosine of x. This is important because it shows how the derivative of sine relates to cosine. but with a negative sign. Moving on, we see do equals 2 times dx, which indicates that u is a function of x, specifically u equals 2x. This is useful because it simplifies the differentiation process when applying substitution. Then, we have do equals 2x times dx, meaning u is x squared in this context, which again helps us handle more complex derivatives through substitution. For dv, we see two options. One is cosine x times dx, and the other is sine x times dx. These represent the derivatives of sine and cosine functions, respectively. Finally, u equals 2x in one case, and u equals x squared in another, reinforcing how different choices of u can simplify our differentiation process. Overall, these points highlight the importance of recognizing the derivatives of basic functions and how choosing the right substitution can make differentiation much more manageable.